we could see these signals. That's not so essential. But I would like to fast forward then to 1999. Here's where we were in 1960, and what happened then was that people thought if these pulse lasers were fun, it would be more fun if the pulses was shorter, because then you could see shorter chemical processes. It would be fun if the pulses were faster. Once in a minute or once in a day is not so fun. But how about 100 million times in a second? That's pretty good. So femtosecond lasers came, and what our team made was control of the lasers, so that if you knew what their frequency is now, you'd be able to know a minute or a second anyway later what it would be. So we'd call that phase stabilization. And I just told you about this magic fiber that has supercontinuum or strong nonlinearities. And that made it possible to have this optical comb. And so we have this 39 years gap when each person is working on something. It's just step ahead. Publish it in the journals. Nobody knows it's really important because it isn't by itself important. It's the building of stuff one by one by one, and then some later person comes along and says, oh, I'm going to take it. It's like having a good Chinese dinner, right? You take something from column A and something from column B, and you can create stuff which is completely amazing by synthesizing this. This was done in a collaboration with Ted Hensch in Munich, Germany, and our group in Boulder. So with these combs available, then we have a light which is simultaneously available as these impulses in time, or simultaneously available as continuous frequencies, because they're there all the time. It's just how do you look at it. So I'd like to explain to you how to think about this comb. Well, it's these individual frequencies. We'd like to have them be equally spaced. So how do we do that? Well, we get our computer and we add up these frequencies, and they're not equally spaced, but they have a common submultiple. So they coalesce here and they partially coalesce here. And okay, here's 3 or 4 of them. And now what happens? Well, here there's 4 or 5 waves that are all strong at the same time, so that's going to add to the power. So let's look at the power. So here's where 4 or 5 waves are coalescing. Here's the next place where they do, and we get a big peak. Now, the waves that I'm talking about are not 4 or 5, they're a million. Take a million waves, and they all get synthesized back together and coalesce at one time. And then where did all the energy go? There's no energy almost all the time, and then it comes at one time. Well, it's way big. It's a million times taller because we added up a million of these little waves, and the energy is a million times, the power is a million times higher, but also it's shorter by a factor of a million, and it is less dense than these continuous waves by a factor of a million. So million squared up and a million times a million down, and so the power is conserved. It's just that the power is delivered in a really short time. So now you see why if you took that kind of light and put it into that glass fiber, the glass fiber says, oh man, and it makes nonlinear interaction. Let me talk to you in a different way about how this is. Some of you are old enough to have gone to a garage before the insurance people got so tough and you couldn't watch your tires get balanced. If we want to measure it and it's turning too fast, what's the method what one uses? Well, it's a stroboscope. It's a flash of light, and it stops this valve from turning. And some of you will have that memory in your mind from going with your dad to just before the vacation. So this is some kind of optical stroboscope. It's just completely the same idea. This is, maybe we'll call it a mega stroboscope, because there's 10 to the 6th or a factor of a million between the strobe rate and the turning rate of this system, where when we do it with tires, the strobe is a few tens in a second and the tire is turning only a some multiple of that. So there's then the way that this rubber and the road are meeting is we go into the lab and we've got a green laser that's on all the time. It's actually the same exact color as this pointer makes. It's made with the same crystal for the oscillator. And its waves are on just like the waves that are in behind the AC power plug. That's 60 oscillations in a second. And if you plug your fingers in quickly, you could even come in when the voltage happened to be 0 and not get a shock. But most likely it takes longer than 120th of a second to plug in, and I can remember that there's some authority behind that. This wave oscillates plus and minus, and it doesn't last very long. One cycle of this, you can see, is 1,000, million, billion, trillion, 0.002 trillionths of a second. That's not very much for one cycle. So no wonder. This is basically the domain of visible light. And on the other hand, if we want to talk about it in things that we can understand, let's demagnify it by 500,000 times. So now we can have these oscillations, and okay, here they are. We can't see the oscillations anymore. It's just continuously always green. That's how it looks, right? It's just always green. But sometimes it's off. And then we have in the lab another laser that makes these pulses, and they're really thin as far as you can see with the lab instrumentation. It's just completely sharp. Well, okay, so how do we get these to be compared? If we look on this in the same fast scale before this magnification, then these things which at our laboratory scale are arbitrarily sharp, they actually can be seen to have a little bit of shape to them. And actually, the way I've drawn this, these two shapes are the same for these two pulses. And even they match up with these other pulses. So the summary of this that one doesn't first understand, but is completely delicious, is that it means that this pulse is occurring at a regular rate, and that this continuous wave is an exact integer multiple of this repetition rate here. So you end up with this factor of 1,000,000. You saw that we had those huge big long lasers, and we had 3 of them, and that's 2 times 2 times 2. In one laboratory we went 8 in frequency. In the next laboratory we actually had 4. We went 8 and times 2. We had 16 times. And we were heading for a factor of 150,000 for that first experiment. Here is a factor of 1,000,000 right in the laboratory, and it'll fit on that table. It is simply a breakthrough. The box that's made by one of Ted Hensch's students costs $250,000, and it's worth every penny. So each pulse has the same shape and time. So in case you've encountered Mr. Fourier, let me just say this, that if you have a single pulse, you have a broad spectrum. If you have repetitive pulses, you get a comb. And if your pulses are combs in time, you get a frequency space, and the longer you measure, the more precise it is. If your combs are in frequency, I showed you they synthesize and you can make combs in time. So the width depends on how many of those you add. So this was understood in the 1970s, but there was no parts for it, and just simply had to wait and work on it. So I brought this to the attention of the International Bureau of Weights and Measures. They had a special seminar just before Christmas in 2000. We had announced this result. And this combined then ultra-stable lasers, ultra-fast lasers, ultra-nonlinear fiber, so continuous and femtosecond tools. So this is a new alliance for getting science done. Part which that happened partly by engineering and partly by good luck is that these young guys that like to do science are very friendly ones. Whether it's the German guy, Thomas Udem from Garching in Munich, or the guy out of my lab, Scott Diddams, they like working together, and so we spent a certain amount of money with United and Lufthansa to get Udem to come to our lab for a couple of weeks and learn what we're doing, and maybe carry some good ideas, and then a week or two later Scott would go there. So this let us have a coherent interaction between these two labs, and no hard feelings about the fact when I was doing something really important. In fact, we're still pals and can meet in some kind of place. I don't know what your style is, but that kind of outdoor palace in Munich is a good place for talking science. If you would like to read about this, my colleagues and I made a paper that discusses this revolutionary kind of laser light, an optical frequency comb. It makes more possible, more precise atomic clocks and other applications. So it's in Scientific American April from last year, a couple of years ago. And if you want to see the professional one, it's in PhysRev Letters. So I've told you about something which is a lot like this Swiss Army knife. Actually, this is kind of sad for me because this Swiss Army knife was just picked off by the TSA gentleman because I was so stupid it was still in my pocket. I forgot to take it out on this trip. What that is a tool for all seasons. Here's another tool. This is a schematic way for you to remember how optical combs work. They make a gear kind of connection between optical domain, where the wavelengths are 1/10 of a 1,000th of a millimeter, up to microwave domain or radio frequency domain. They gear it together, and so now we're making a transition. I've told you about this epoch. This is the year 2000, and that passes. New stuff happens, and in particular, new energy comes in. Dr. Jun Yi, if you're really, really lucky, you'll sometime work with a person like Dr. Yi. He's got more ideas than just ideas every place. And here's the stuff that he's done in less than 10 years. I mean, for example, how about looking for planets? Or how about looking for gravity? Or how about looking for just all kinds of really important stuff has come out of this. Nobody had any idea that it was going to be there. Let me just go through a couple of these quickly. And so I'm going to tell you a little bit about atomic clocks. Our ones in the Gila building are running on strontium atoms. And through this effectively gear that the comb provides, we can connect onto some laser whose wavelength will fit into the fiber that goes under the city, comes out over in the labs of the National Institute of Standards and Technology, where they prefer calcium or mercury or some other. They gear it to the same place so we can measure it. And that's important because if you would like to have two labs doing this kind of work and you just send your light in the optical fiber, you send out something which is really sharp and it gets to them and it's really broad. If they send it back to you, it's even broader. And we submitted a patent application for how to do this, to cancel the noise off. Go out, come back, it's got a lot of noise on it, measure the noise, divide it in half, put a minus sign in it, send it out. So we know what the fiber is going to do for a little bit, and we put a minus sign in by that much noise, and when we get to the far end, it's clean again, and it's really clean. It's super sharp. So now in two laboratories a few kilometers apart, you can have the same frequency stability. I show you this picture just because it actually has a little technology. Every place you see a padlock, you should think of circuit board, graduate student putting electronic components in, soldering that all up, getting it working, and maybe a couple of weeks or possibly even a month for one of these hard ones. But finally this works, and it's kind of like a rental car now. You don't need to think about anything. You push the button or put in the key and it just goes. So this comb has a representation of either time domain or frequency domain. And if you put it into the fiber at NIST and you send it over to Gila, no, I guess I've drawn it the other way. We send it into the fiber under the ground at Gila and it gets to NIST and we measure what we have, and it is really narrow. So this is 1 cycle per second is the variation. And the number of cycles, so that's the variation, 1. And the frequency itself is 560, and now 12 more zeros. So it's very, very sharply defined. And a good place to use that would be if you have all the nations of the earth building a telescope array for millimeter waves in Chile. So on the high mountain, these telescopes cover 100 square kilometers, and they're almost ready to work in the way that they're synchronized so that you can look in a coherent way at extraterrestrial signals, is you have fibers between these. You can transmit frequency standards between your own place, and in Germany they've gone from North Germany even to South Germany with this kind of precision. If you look with these super stable lasers and ask an atom how narrow should it be, we measure that it's less than 1 hertz. The atom thinks that it's 1.8 hertz wide. Well, okay, that's maybe it's due to some difficulties in one place or another, but it's not completely bad. It shows that it almost is available to be using. I'd like to go quickly now through about building optical clocks with this. If you measure that frequency, it's the same. You just keep making these measurements, it doesn't change. If you study what makes it change, now we're here in this making bins that are only a couple tenths of 1 cycle per second wide, hertz. And there's nothing much going on and you can understand it. So here's frequencies. This is now the best precision that mankind has ever had for making measurements. It's on time or frequency. If you like time, here is billionths of a second for 1 day of drifting. And when atomic clocks first started, we were using the Earth and the spin of the Earth, and that was a little bit unstable because we would have storms. The National Bureau of Standards, 1, 2, 3, all these things, and then the fountain technology came, and so that made things better. Another technology that came was this laser cooling. And so our optical clocks, I showed you a whole bunch of them, and they have really improved. And so after 2000, well, our cesium guys did another point. They, by that time, had mercury working. They could do a point. Here's our strontium point. So now we're talking about 16 digits of meaning for this, and that's really a completely amazing place to be. So I'll go quickly through this. We have the electric clock, we have a fountain clock, we have the laser, and finally we have this one single mercury ion. A name to remember about this clock is Jim Berquist. He's a super good guy, happened to be one of my graduate students. I'm quite proud of him. Now let's see. So where are we now? For 59 years, cesium clock has been the best standard of anything, and it enables us to understand the international second and the unit of frequency. So over 60 years since this clock was introduced, we've improved by a factor of 1 million. So that's 10 times improvement each 10 years. So now we have 16 digits with the fountain. And what's happened in 2008 is that 3 optical clocks are already better than that. So you can already smell the toast. This is, cesium is toast, and optical clocks are going to be what it's at. Lots of atoms and things to choose. But then you start thinking, man, that's really cool. We've got all of these things. You know, I wonder if they all keep time at the same rate. Maybe there is something about physics that we haven't thought about. That could be. So that topic is cosmology. In the laboratory, we can do cosmology experiments. So here is one way to do it. You compare 2 different optical sources, Berquist and his colleagues. One of them is based on mercury, one of them is based on aluminum. Use a comb to make the comparison possible. And here's the summary of that. There could be a frequency shift for 2 reasons. One of them is that the magnetic moment of cesium would change, and that's this axis. And another axis is that some special number in quantum mechanics is called fine structure constant. And it's got electric charge, Planck's constant, mass of the electron, and the speed of light in it. It's a pretty harmless thing, and we know its value. Its value is 1 divided by 139 035 999 8, and we know it to plus minus 2 in the 8th place. And we don't know whether that number should be 137 or 14 or 2 or anything. There's no theory about it. So this is really an interesting thing to measure and see if it changes. So here's these guys from 2006 to 2007, and they're measuring this frequency ratio. And I don't know what your taste is, but I would say this looks interesting. The data doesn't support a definitive statement. It's just as good statistically to have a straight line, oh, no change, just totally boring, go on, don't think about it. But, you know, maybe this is tilting. So the time when you guys are out is going to be fantastic. We're going to find out, is this Big Bang, it happened, then we came out, and one of the ideas is that there was expansion so fast that there could be universes that formed besides ours that we don't know about. And it's just boggling to think about it. I'd like to tell you something which I'm sure that you will come into contact with. This is the business of finding out about molecules that are in a gas. So here's the comb coming in. The bouncing time in this between these mirrors is just the same as the repeating speed of these pulses. So they just can keep coming in and keep adding. Some molecules in air go through between these mirrors, and because the light goes back and forth a zillion times, around 100,000 times, if this molecule absorbs even a teeny bit, it's going to take light out. And if we disperse it later, then we'll see the absorbed light. So here's where one molecule went, and maybe this plus this is where another molecule absorbed. And you can't see it, but this is really those million of comb lines that I was talking about before. So this is an optical comb. And you have some guy who's not feeling totally healthy. He actually looks kind of green in the picture, and he blows his breath into some bag that doesn't mess with it. And then that is pumped slowly through this gas cell, and a little pump takes it away. The fiber laser makes light to go through this cell, and it's dispersed, and some infrared camera can see it. And what you see out of that across this wavelength range, 1.6, so this is basically the band that's covered by the telecommunications fiber stuff. And you see molecules that you know and we love, and for example, they're carbon dioxide. So that's what these molecules are. And of course, we can see water, and we can see methane coming out of humans. So that's kind of interesting. But another interesting thing is that the isotopes, the carbon-12 or carbon-13 or oxygen-18, those are relatively rare. There's only 1%. But you see these lines are all the same strength. So I can basically promise you that in some time, and I don't know how long it is, it will come out that human bodies are getting rid of these isotopes that we don't normally use, or somehow we're messing with the isotope ratios. An application for this is in the asthma or disease which is called sudden acute respiratory distress syndrome. It happens to folks who have been in the war in Iraq. And it is to be analyzed by these fellows who are in the hospital. This is a self-immune reaction, and it takes the person only 6 hours or so to pass. So it's terribly important, and it's hard to get money to do this because the doctors say there's no papers that use this technology, and the scientists say, how do you know that it will measure anything that's important for medicine? But anyway, it's something we finally have been funded. We can see ethane that comes from cancer. We can see ammonia a year before people have kidney failure. So it's going to be important. It could be made for around $50,000. Doctor could buy it, and I guess in addition to having blood sample when you go in for your yearly checkup, you'll 5 years from now you will have a breath sample made as well. I don't know how you make money out of this because there's no ink cartridge that you have to keep buying. This is just one apparatus. Okay, I'm going to conclude then with talking about using this tool for fundamental physics. If you visit my tool store, I'm going to sell you a comb, of course. and it gives you 15 digits, but now it's 16 digits, and it really represents a great highway, and we only know the first couple of neighbor stops on here that I've showed you what it is. Here's a highway which would be fun to apply this to. There's a place in the sky which looks like it's dark. Even with Hubble, it looks like it's dark. And the young lady scientist said, wow, that's kind of interesting. I would like some time to point the Hubble to that. So you get Hubble time in hours, or 2 hours maybe if you really have big money. So she got 2 hours, look, nothing. And she says, I really believe in this. The Hubble gyros are so good I can point the same direction. Let's do this again. Got to 10 hours. And then you could start seeing what there is out there. So this is looking back in time to 5% of the age of the universe. And what you see is stuff which is a little bit like what we have, and in some ways it's different, because the spectral lines in these stars don't show up at the place that they should. We know that from Hubble that everything is flowing out, because we did have a Big Bang after all, and so this is going out, and any place that you look, it's going away from us. Okay, fine, that's the Hubble flow. Now this is going out faster than that, and so that is an interesting thing. And another thing which is interesting is that we can see even in our own galaxy is that these galaxy arms stay on there, and if you look with the Doppler shift of the wavelengths, this thing is rotating so fast that these arms would fly out, just like the kid on the merry-go-round falls off if he doesn't have a strong enough grip. That's really interesting, because it acts like there's some extra mass that's not making light, but is making gravity. So this is kind of a mystery, and this is called dark matter, and in fact, if you count it up, 80% of what there is dark matter. It's holding these stars and the stars in our galaxy together. And now I mentioned that we have this dark energy that's exploding this out even faster than it was before. Oh, and that's even more. That's 75% of the energy. So that means we have to revise this. So dark matter is 20%, and us, piddly 5%. We don't know about what most of the stuff is in the universe. Now, I can't imagine a better time to go as a young person into science. I'm a little sorry that my mother started me so early, because the next years are going to be fantastic. Now, that really means that it's fun to check our assumptions. So you've heard about string theory. It works well in 10 dimensions. I mentioned the possibility that there's a multi-universe. There could be another universe that is edgewise to us, hardly shows up in our place, makes little bumps maybe. So those are called brains out of membrane. But it's sensible to worry a little about this, because if you think about this number of pi, which our Greek friends had, the circumference divided by 2 times the radius, or the diameter. Now, if you do this on a non-flat surface, then the circumference around this ring is less than you would get if you measured the diameter from the center out to the edge. And so that means space would be distorted, because we know that there's gravity fields, and that distorts the space. So this makes it really interesting. And the last thing that I'll show you then is an advertising poster for our project called oh man, I've got to be faster with an acronym than that if I go to NASA and try to get our money again. This is, yeah, okay, I'll find it in a second. The way we're going to find out if space is the same in all directions is we're going to drill a block of low expansion glass this way. And the space-time anisotropy research, yes! And there are going to be mirrors on the end of this, so the light will bounce back and forth in this one, in this one, in this one. And that's this top block, here's the bottom block. In the middle, we're going to have a gas cell. So this is light going in vacuum, light going in the gas, either on this ricochet path, or maybe with paths like this that bounce back and forth with multiple dots on the mirrors. that will be my atomic clock, and we're going to compare atomic clocks with the speed of light clocks that are there. And this is, I think, is one of the coolest experiments. So it was funded for research until we ran out of money during the previous president's term, and he canceled all the science in that. So there's lots of issues to think about, whether we're doing the research the best we can, the education part, and that's what Lindy and I are so much about, and what I see the faculty of your university are concerned with. One thing which I didn't understand is the importance of balancing family life and research. And it's only that my wife's good spirit that she finally, I think perhaps with the aid of something like a 2x4, came to me and said, dude, this is not fun anymore. I've been married to you for 45 years and you've been home for 2 hours. What is the deal? And so I finally started coming home for dinner when it's the right time and so on. There's some very interesting questions to talk about. The people of one country make money available, scientists do research, they publish their papers in scientific journals, and then some private company maybe charges for you to use that journal. That makes me cross. What we're doing now is exactly what we have today. We're going to places, talking to kids, all ages. Lindy has a nice website for learning about these kinds of things. If you're interested, I could show a couple of pictures about that particular experience. So I thank you for your patience. I've talked completely too long, and way too fast. Too many ideas are showing, but the main thing is it's just so exciting to see all the possibilities that are there. Jun Yi has a very good website. You can have a look on that. Lindy's place is SciTech's Discovery Program for Kids. If you want to read what the NIST colleagues are doing, it's that. And if you'd like to catch up on the 50 years of lasers, the Optical Society has another. So thank you very much for inviting me, and I appreciate your attention.
At this time, we will have questions and answers.
At least questions are possible. I'm not sure about the answers. Please.
So what inspired your research in lasers?
My research in lasers wasn't inspired by lasers, because the magnetic resonance with microwaves was what came before this. And that's kind of a leftover because we had this war in the 1940s and microwaves were important for radar. And so then that was the hottest, the latest hot stuff in that. And so a young power kid comes up, yeah, well, man, I'm going to study microwaves. And then crystals were starting to be important because you could do stuff with crystals. So then how about we change the crystal in some way and use microwaves to study that? So I had an X-ray machine and we turned the crystal color. So that, and then basically the highway is, you look and you're at a crossroads and there's a nice view down each one of these. I have just been super lucky.
When you ask your question, can you please come to the microphone and say your name and your major? Thank you.
I'm Jamal Phillips, industrial technology major, and I was just wondering, what are some of the practical applications in your research that need further study?
And so that's a question of where we come to mean practical. I think this medical application is something which is intensely practical. We have a diagnostic that reads different parameters of the metabolism, and we have very fast, a few breaths in a minute kind of information about what's happening. So that's something which just needs money from a venture capitalist or something like that, and that could happen. But there's a bit of a struggle because even the university can realize that there might be some financial consequences of success on that highway. So you know how they're going to play with. So it'll happen. In the measurement science is another place where the impact is big. And you have something like this that you can control the TV with. And I've now have experience with a car that has one of those for turning its engine on, which just shows I like old cars. So radio and wireless and infrared, they certainly have practical applications. And the last topic is something about the efficiency of doing science and how friendly and powerful it is when it's transnational. So, for many years during the time of the big contest with the former Soviet Union colleagues, I think I had as good a contact with that guy, Veniamin Chebotayev, as I did with the management system on our side. And he came to the place where we had a tunnel and were measuring seismic waves in the earth. A lot of the seismic waves are caused by small earthquakes or bigger earthquakes. Some of them are caused by special things which people have planned, like testing nuclear weapons. So we had a contact that way, and he knew what we were able to achieve. And so I really feel I've made a small contribution to the stability during those 50 years of communication scientist to scientist about stuff which was simply technical. Knowing what's important, for example, let me give you the other example. Here is my friend, now 90 years old, who thought his life had been a failure, roughly speaking. He just barely got out with his skin from Holland when the Germans were there. He came to the United States, was immigrated, and refugee status in the U.S. Harvard recognized that he was extra smart, and they had him doing that nuclear magnetic resonance research. Okay, that's pretty nice stuff, and that would give a paper and then another paper, and so there was papers over all these years. And then in the 1990s, some people realized that, oh, we could use that process to make images. And I guess it was before that, because I had a bicycle accident and had an MRI of my back in 1980 something. So that is really a practical use, and there's no way in the world that one would know enough to be able to plan that. So my advice for the government is that they should fund stuff which is high grade, that people are really working hard on, that other scientists think is valuable, and it's powered by curiosity. Because the government could lose the money if they give it to a guy who's doing something, but they get more money next year. It really doesn't matter. But that guy's life, that 1 year, that's really important. And the smarter the guy is, the more he's worried about that problem. So I think it just works out. It somehow is an issue about trust that people. I mean, I pay my taxes. I think some of the money is used in a good way. I don't know. We need to sit in a quiet place and talk for some hours to get a good answer for this, I think.
All right. We would like to thank you, Dr. Hall, for your presentation. Now we will have closing comments by Dr. Mortazavi.
First of all, I want to thank you, but I'm going to actually, instead, I'm going to give a short story. When I was doing my PhD, I did similar to Dr. Hall laser cavity with such absorbers. One time, of course, we had problem with laser stability. One time, my advisor told me, who worked with Dr. Hall, he told me, Mansour, you know, Dr. Hall is very smart, very sharp. One of these days, he's going to get Nobel Prize. And that was sometime in late 1980. And the person was Professor Singh.
Oh, really?
Yeah, yes. So we want to thank you, and I always looked at your literature, and we thank you for coming here. Please, Dr. Benjamin.
It's our pleasure.
Thank you, Dr. Mortazavi. Audience, we have been in the presence of a genius. He is so knowledgeable. in so many areas that we could be here all day and tomorrow and still be learning. But we so appreciate your coming, and Dr. Hall, whenever someone comes to the state of Arkansas, and especially to UAPB, we want to give that person something to take home to remember us. And so if you will come back, we would like to present this to you. It's shaped like the state of Arkansas.
It's beautiful.
It is in appreciation of your serving as a guest lecturer here at the University of Arkansas at Pine Bluff for the UAPB STEM Academy on this day in 2011.
Well, thank you so much.
And
That's beautiful.
you are so welcome. And we want to make sure we get a picture of you and your wife on the end of this with the plaque,
Okay,
so
that's
that we
good.
will put it in our archives here at the university. Thank you so much.
Thank you.
And we would also like to recognize Mr. Al Ashley, if you would come forward, because you play such a critical role in helping us to make the right connection and to get on the road, not the one that he was talking about, but to get on the road to this great lecture today. So Mr. Ashley, as you're coming forward, this is presented to you for your dedicated service to the UAPB STEM Scholars Academy. And this is signed by our Chancellor, and thank you so much.
And thank you very much.
He not only helped us make this connection, but and I want to say this because we have some people here that might not know, he has been very helpful to us in getting international internships for our students. We are so appreciative.
Thank you.
Okay? And with that said, we want to thank you again for coming. Some of you will be having lunch with our guests. We are going to head right in that direction. And this has been a great opportunity, and your presence, the presence of each one of you, has made a difference in terms of this event. Thank you so much, and enjoy the rest of your day.